Up to this point in the chapter, we've really just focused on the transition metals by themselves, the properties of them, how they behave, their valence electrons, and things like that. What's really going to be different about this chapter is looking at how those transition metals form complexes and the chemistry behind them. What we're heading into is a lot of information about something called coordination compounds. And these are compounds in which the central metal ion or atom is attached to a group of surrounding molecules by a coordinate covalent bond. Now remember, coordinate covalent bonds are different than regular covalent bonds in that both electrons in the bond were donated by the same atom. In a quote-unquote regular covalent bond, we end up with one electron donated by each atom involved in the bond. In this case, they both come from the same atom. So here is an example of a coordination compound, or a coordination complex, we often call it. I've left off a little bit of information, so let me just add it here. We have a nickel 2+ ion here in the middle. So this is our transition metal, and it has been coordinated by 6 water molecules. And so we call this a hexa 6 aqua water nickel 2 ion. The whole coordination compound is an ion. And in the other images that you can see on page 854 shows you a picture. You can kind of see that it has an octahedral geometry. We'll talk about that more later. And it's labeled those oxygen atoms as ligand donor atoms. We're going to talk about that more in the next slide. Now, I've alluded to this before, but a lot of these coordination complexes make really pretty colored solutions, or really pretty colors as the solids. And so the third picture in this image is the really pretty green color of this hexa aqua nickel 2 ion. Now we need to do some labeling within our coordination complex. The first thing we need to label is the ligand. Ligands are ions or molecules that are bound to metal ions via coordinate covalent bonding. Again, that means that one atom donated both of the electrons in the bond. So in this same example of the hexa aqua nickel 2 complex that we saw on the previous slide, we've got water is our ligand. 6 of them, as a matter of fact, but we want to specify that each water molecule is acting as a ligand. Now that's a little bit different than the ligand donor atom. So what we're doing here is differentiating between the entire ion or molecule that acts as the ligand and the specific atom in the ligand that donates the electrons. That's the thing that's that's the atom in the molecule that's physically bonded to the metal. So in this case, for each of our water molecules, the ligand donor atom is oxygen. Now what we're going to find is that some ligands have more than one ligand donor atom, and that's going to be really important later. We'll see why when we talk about something called a coordination number. But for now, let's just differentiate between the ligand, the entire molecular ion that bonds to the metal through coordinate covalent bonding, and the ligand donor atom, which is the specific atom in the ligand that does the electron donating. My use of the word electron donating in the previous slide probably clued you into the fact that coordination compound formation is just Lewis acid-base chemistry. Effectively, our metal ion is acting as our Lewis acid. It's the electron pair donor, the electron pair acceptor. The metal ion is the Lewis acid, the electron pair acceptor, and the ligand is the Lewis base. It's the electron pair donor. So our entire coordination compound is formed via a Lewis acid-base reaction. I've already shown you an example of a coordination compound that was an ion, and as with many ions, sometimes we add a counter ion to turn it into a salt, an ionic compound. So here's the same nickel hexa aqua, that just means 6 waters, complex that I showed you before. If you remember from before, it had a 2+ charge. Now, later on in the chapter, we're going to figure out how to determine the charge on the complex, how to determine the charge on the metal ion from the charge on the complex, and things like that. For right now, let's just recall that this was present as a 2+. ion. And so we can add a 2- sulfate ion, SO4 2-, to balance out that charge. So the entire thing is now a salt in which the coordination complex was a cation, and we added a counter anion to balance it out. Just like in any other salt, we always write these in the order of cation and then anion. Now here's another example down below in which the coordination complex is actually present as the anion. We can tell because it's written second. And if we think about the fact that potassium has a 1+ charge, and there are 3 of them, we have counter ions that total to a +3 charge, which means that our anion, our coordination complex, must have been present with a -3 charge. So you'll see these either way. When you see a metal cation out front, you know that your coordination complex is present as an anion, and when you see the coordination complex out front, you know that it's present as the cation. Note that the coordination complex itself is always shown in those square brackets, and so that's going to help set it off for you so that you can tell the difference between the counter ions outside of the brackets and the ligands inside the brackets. That's actually a really key important point, so let me say it one more time. Inside the brackets, those are your those are your ligands. Outside of the brackets, those are the counter ions. One of the things we'll look at a lot in this chapter is the coordination number. We're going to define the coordination number very specifically. It's the number of ligand donor atoms that surround a central metal ion in a complex. Let me underline that. Ligand donor atoms. It's not the number of ligands necessarily. It's the number of ligand donor atoms. The number can range from 2 to 12. Very commonly it's going to be 4 or 6. And this table 20.4 in your book shows you examples of complexes with coordination numbers 2 through 8. I've just highlighted 2 through 6 because, again, those are more common. And so you can see we've got a silver and ammonium. So ammonia is acting as the ligand here. Chloride is the ligand. Here the cyanide ion. Ammonia again, water, cyanide. All of these are, in all of these cases, the number of ligands is the coordination number. But very shortly we're going to look at some ligands that have more than one ligand donor atom per molecule. So again, I really want to emphasize the coordination number is the number of ligand donor atoms that surrounds the central atom. So when we look at a picture, it should be pretty clear. If we go back and look at that hexaquanickel complex, you very clearly saw 6 things bonded to that nitrogen or that nickel, So that's really what we're counting. In order to tell just from the formula, we're going to need to be able to know how many ligand donor atoms there are per ligand, and that's something that we'll look at a little bit later in this chapter.